Everyone, I am Sachin Sarve presenting PPT design of different oscillator circuits. In this PPTs, we will see basically the crystal oscillators and unijunction oscillators. In previous PPT, we had seen the RC oscillators, LC oscillators, and their types, their design also, and their numericals and some design numericals. So first, we will see the crystal oscillator. So crystal oscillator is a combination of RL and C, resistance, capacitance, and inductance. A crystal oscillator is basically tuned circuit oscillator using a piezoelectric crystal as a resonant tank circuit. The crystal, usually quartz, has a greater stability in holding constant at whatever frequency the crystal is originally cut to operate. Crystal oscillators are used whenever great stability is required, such as communication transmitter. So this is the diagram of the crystal, the resistance, inductance and capacitance, and this is Cm, that is electrical equivalent circuit of a crystal. The quartz crystal exhibits the property that when mechanical stress is applied across one set of its faces, the difference of potential develops across the opposite faces. This property of crystal is called as piezoelectric effect. Similarly, a voltage applied across one set of faces, the crystal causes mechanical distortion in the crystal shape. When alternating voltage is applied to the crystal and get the mechanical vibration or set up this vibration, the inductor L, the capacitor, represent the electrical equivalent of crystal mass compliance respectively, whereas the resistance R is an the electrical equivalent of the crystal structure of the internal friction. The shunt capacitance, that is Cm, that represent the capacitance due to mechanical mounting of the crystal, because the crystal losses represented by R and small equivalent crystal Q, that is quality factor, is typically very high, that is 20,000. This crystal is represented by equivalent circuit, that is shown in figure, that is we previously seen, that can be two resonant frequencies. One resonant condition occurs when the reactance of series RLC is like or equal and opposite, and for this condition the series resonant impedance is very low, that is equals to R. The other resonant condition occur at a higher frequency when the reactance of the series resonant leg equals to reactance of capacitor Cm. This is the parallel resonance or condition. The impedance versus frequency of the crystal, that is shown in this figure. Then series resonance circuit. So here we use the crystal control oscillator in series feedback path, that is connected to the CC coupling capacitor. This is using the BJT R1 R2, that is the biasing capacitor, and we use the choke at the collector side. Then RA emitter resistance and C is the bypass capacitor. In the series resonant mode, it may be connected as a series element feedback path. At the series resonant frequency of the crystal, its impedance is smallest and amount of positive feedback is largest. A typical transistor circuit that is shown, or the BJT, using BJT circuit. Here R1 and R2 and RE provided the voltage divider stabilized DC bias circuit. The capacity C provide the AC bypass of the emitter. RFC, that is the coil, provides the DC bias and AC signal on the power lines from affecting the output signal. If the collector to base is maximum when the impedance is minimum, the coupling capacitor CC has negligible impedance at the circuit opening frequency, operating frequency, but blocks any DC between collector and base. The resulting circuit frequency of the oscillation is set then by series resonant frequency of the crystal. It changes in the power supply voltage, transistor device parameter, and so have no effect on the circuit operating frequency, which held the stabilized by the crystal. The circuit frequency stability is set by crystal frequency stability, and which is good. Now this is the diagram of parallel resonant circuit. In parallel resonant circuit, R1 R2, that is voltage divider biasing, then RS, then C1 C2 XTL, that is crystal, is parallel at the output side. This is crystal control oscillator operating in parallel resonant mode. Since the parallel resonant impedance of a crystal is a maximum value, it connected in shunt. At the parallel resonant operating frequency, the crystal appears as the inductive reactance of a largest value, that is shown in figure, connected as an inductor element in a modified Colpit oscillator, and maximum voltage is developed across the crystal as its parallel resonant frequency. This voltage is coupled to the emitter by a capacitor. This is the Miller crystal control oscillators. Here is the FET is used, gate resistance, choke, RS, inductance, that is also the choke, and variable capacitance C, that is connected to that, or parallel. A Miller crystal control oscillator circuit, that is shown. Tune LC circuit in the drain section, that is showing in the drain section, and adjusted near the crystal parallel resonant frequency. The maximum gate source signal occurs at the crystal, that is anti-resonant frequency, and controlling the circuit operating frequency. Now we will see the details of the crystal oscillator. Here we use the op-amp in the amplifier. In the non-inverting mode, we apply the crystal series with the 0.1 microfarad capacitors. Then RF is 100 kilo ohm. Input resistance, or R1 is the 1 kilo ohm. And op-amp can be used as a crystal oscillator. The crystal is connected in a series resonant path and operates at the crystal series resonant frequency. The present circuit has a high gain so that the output square wave signal result as shown in figure. Now next, that is the unijunction oscillators. Here we use the basic use of unijunction oscillator circuit. Here B1, B2 and E, RT, CT, R1 and R2. So we are getting the voltage VB2 and VB1. A particular device, unijunction transistor, can be used as a single stage oscillator circuit to provide the pulse signal suitable for digital circuit. We use in digital circuit applications. The UJT can be used in what is called as relaxation oscillator, that is shown in the basic circuit. The resistor RT and capacitor CT are timing components that sets the circuit oscillating rate. This frequency may be calculated using equation, that is the f0 equals to 1 by RTCT ln into 1 by 1 minus zeta. Typically a unijunction transistor has stand-up ratios, that is 0.4 to 0.6, and theta, that is the 0.5. So that is frequency equals to 1 by RTCT ln 1 by 1 minus 0.5. If you put the value of zeta is 0.5, so finally we will get the 1.5 by RTCT. So that capacitor CT is charged through the resistor RT towards the supply voltage VBB. As long as the capacitor is below the stand-up voltage or VP set by voltage across B1 and B2 or B1 minus B2, and transistor stand-up ratio, that is VP equals to N zeta or VB1 minus VB2 by drain voltage VD. The unijunction emitter leads appear as the open circuit when the emitter voltage across capacitor C exceeds this value VP or pinch voltage. The unijunction circuit fires the discharging the capacitor, after which new charge cycle begins. When the unijunction fires, a voltage rise in developed across R1 and voltage drop developed across R2. So that is showing in the diagram. V equals to Vp, then with respect to times. So initially it is 0 volt, so that is falling edge, and rising edge, that is the unijunction oscillator waveforms. Now these are the basic formulas or important formulas that we studied the previous PPTs. We studied the phase shift oscillator. The formula of phase shift oscillator, that is resonant frequency, is calculated by 1 by 2 pi RC into under root of 6. On that time the beta, that is the feedback network element, 1 by 29. Similarly, Wien bridge oscillators, that is f0 equals to 1 by 2 pi under root R1 C1 into R2 C2, or we can say under root of R1 C1 or 2 pi RC. So these are the under the types, that is the RC oscillators. Then Colpitts and Harty oscillator, that is in the LC oscillators. In Colpitts, f0 equals to 1 by 2 pi under root of LC equivalent. C equivalent can be calculated by C1 C2 divided by C1 plus C2. Harty oscillators, 1 by 2 pi L equivalent to C, where L equivalent can be calculated L1 plus L2 plus twice M, that is mutual inductance. Then unijunction oscillators, that is f0 equals to 1 by RTCT ln 1 by 1 minus zeta. So thank you.